Hello everyone, my name is Farezky Millian, and
And my name is Hayurani Nugraha.
and today we're gonna explain weak bases and base ionization constant in the chapter of acid and bases. Okay,
Okay. Okay, so in this subchapter, the ionization of weak bases is treated in the same way as the ionization of weak acids, which, for example, is when the ammonia dissolves in water and it undergoes the reaction. So here are the reactions that is for the example, and the equilibrium constant is given by K NH4 plus OH minus over NH3 H2O.
okay. I wanna add the main idea of the subchapter, and it is most acids and bases do not completely break apart in war. Instead, they get stuck in a dynamic tug of war called equilibrium, and we have to use a specific constant, or in this case KB, because we're talking about bases, to calculate the calculation. And then next, KB here is equals to K to and the constant, which is H2O, and it equals to the formula before. And then because the KB what we're using in the KB here is ammonia. Go down to the graph. Because it's ammonia, that's where we get the 1.8 times 10 to the power of -5. Okay, go up, go up, go up. Okay, so basically that's the main idea here. Let's go to the example 15.10. Okay, in the example 15.10, what we're trying to find is the pH of 0.4 moles of ammonia solution. And then the way we do it is, okay, go down. Okay, the way we do it, we find the equilibrium equation first, and then we find the initial moles, and then because what we get is the ammonia moles, we write 0.4 here, and then we don't know the solution of the moles of NH4 and OH, so we're at zero here, and then because we don't know the X, we just write it as X here for the changes. And then because the one getting ionized is the right one, we use addition and subtraction in the left one. So it equals to the equilibrium is 0.4 minus x. And then the equilibrium for the ionized one is x because that's what we know. And then we put this into the formula, which is Kb equals to NH.4 times OH times NH3. If we write it will become KB equals to x times x, which is x squared, and then 0.4 minus x because that's the ammonia KB. And then, yeah, as we know before, the KB is 1.8 times the 10 to -5. Okay.
Uh, okay, so I'm going to continue the steps. After we found the KB, not yet, yeah. After we found the KB, we can apply the approximation of 0.4D minus x. So we can obtain 1.8 times 10 to the power of -5 equals to x squared over 0.4D minus x. And then the results that we got is x equals to 2.7 times 10 to the power of -3 mole. And then to test the approximation, we need to multiply them by 100%. And the results that we got is 0.68%. And the approximation that we got is valid, so we can continue to the next step, which is at equilibrium, the OH minus is 2.7 times to the power of -3 mole. And then we can continue to find the POH, which is using the minus log formula, and then we input the OH minus in here. So the result that we got is 2.57. And lastly, we need to find the pH for this problem. Actually, the formula for the pH is pH plus POH equals to 14. But in this case, we got the POH first, and then we don't get the pH. So to find the pH, we need to use the POH and also the 14 indicator. And that's why we subtract it, become 11.43, and that is base.
Okay, before we end, I want to add something, and that is we need to remember that the X here is not the pH, but only the concentration of hydroxide ions, or in here is OH negative. And then, yeah, we need to remember that we need to use this formula to get the pH. Okay. Okay, I think that's it from our presentation about the subchapter of the basis ionized constant. Okay, I think that's all. Thank you.